Okay, now we are on tube now. I will start with a brief introduction. So today we are very honored to have Professor Tao Fu to give a presentation on bubble dynamics in parallel microchannels. So Dr. Fu is a professor of chemical engineering at the Tianjin University of China. Dr. Fu obtained his bachelor degree from East China University of Science and Technology in 2005, majoring in chemical engineering and technology. After then, Dr. Fu spent 5 years in studying chemical engineering at Tianjin University for his PhD degree. During this period, he spent about 2 years in Institut National Polytechnique de Lorraine, France, for a joint PhD program with Tianjin University. From 2010, he joined the faculty of Tianjin University as an assistant professor and then was promoted as associate professor in 2013 and then professor in 2021. During September 2015 to September 2016, he visited Professor Ronald Gary Narson's group at the University of Michigan as a visitor scholar. So his research interests include fluid chemistry and microfluidics, interfacial transport phenomena, fluid mechanics at microscale, multiphase flow, and complex fluids. So he already published more than 120 peer-reviewed articles. So Dr. Fu was elected as one of the 2019 class of influent research by industry and engineering chemistry research. So Dr. Fu, please take over the stage and start your presentation.
Okay, thank you very much, Dr. Lee. Thanks for the invitation and the introduction. And can you see the slide clearly?
Yes.
Great, yeah, okay, so I can go ahead. So my name is Tao Fu, come from Tianjin University. So I'm glad to share with you the bubble dynamics in parallel microchannels. So due to high energy and resources consumption and pollution, chemical engineering is challenging. So we need more faster, safer, and smaller processes. So microchemical engineering and the technology is one of the new processes and the technology due to these advantages, such as the way for the scaling up. Here we have lumbering up process and a highly integrated and high surface over volume ratio and easy to control and more flexible. And in addition, they also have high heat and mass transfer efficiency due to high surface over volume ratio. So we can do reaction and separation in micro devices such as microchannels faster and have low energy consumption with less pollution. And for reaction, we usually have great selectivity and high selectivity. And so they have applications in synthesis of new materials and in clinical medicine and in environmental protection. So in these applications, gas-liquid two-phase flow are always encountered in the application. So for example, we usually have bubbles in oxidation reaction. So this kind of reaction, we usually have oxygen to react with other materials. And in another example, for example, CO2 capture, for this process, for example, we use option unit operation to capture CO2. So in this way, we have gas-liquid two-phase flow, and usually we have bubbles. And we for H2 hydrogenation reaction, we usually have we also have bubbles and the gas-liquid two-phase flow. So it's very important to study gas-liquid two-phase flow and the bubbles in microdevices such as microchannels to take advantage of the microchemical engineering and the technology. And in microchemical engineering and the technology, we usually do scaling up by using lumbering up to increase the number of microchannels in this way, from one microchannel to hundreds and thousands of microchannels to increase the mass product of the target product. So if we can control the reaction and the separation process in a single microchannel, do the same thing in these microchannels. So it's quite easy to increase the number of microchannels to increase the mass the mass production of the product. So in number up process, we usually have these two rules. The first one, we usually do fluid distribution at first. So fluids are first distributed to each microchannel, and then they contact with each other. For example, if we do gas and liquid two-phase flow, we first distribute gas and the liquid individually into microchannels and then make them contact, have reaction and separation. So in this way, we need to design the distributor, and we need to pay attention to the distribution of single phase flow and the distribution of gas liquid or liquid liquid two-phase flow. So another way we can at first make contact of gas and the liquid with a certain geometry of the microchannel to have, for example, gas liquid two-phase flow, to have bubbles. And then we can make a product split in a certain geometry, such as T-junction and the Y-junction, to make bubbles break up at these junctions. So in this way, we have to do have to study breakup of bubbles and droplets at T-junction or Y-junctions. So in the lumbering up process, we usually have to design the parallel microchannels. We can learn from nature. For example, here we can use bionic principles to follow Moore's law to design the size of the microchannels. Here we have the mother channel and we have daughter channels. And if we follow this rule, we can have uniform distribution of fluids in this way. So it's important to study distribution of fluids in, for example, here distributors or T-junction and the Y-junctions during the lumbering up. In addition, during the application, we usually have complex fluids. So for example, in drug extraction, agricultural production, and drug delivery and oil recovery, we usually have complex fluids. So these fluids can be classified into highly viscous fluids and viscoelastic fluids, shear-thinning fluids, and yield stress fluids. So if we have complex fluids, we have to consider the property of the complex fluids during the distribution process for gas and the liquid two-phase flow in parallel microchannels. So it's very important to study gas liquid two-phase flow involving complex fluids in parallel microchannels for this kind of application. So this study, we would like to share the gas-liquid two-phase flow and the bubbles in parallel microchannels involving complex fluids. So here, the first case we would like to share is the parallel microchannel with two parallel microchannels with symmetrical geometry, like this on the left here. We have two parallel microchannels here, this microchannel 1 and the microchannel 2. And we have symmetrical geometry for the distribution of gas and liquid. So here we have the distribution of gas, and here we have distribution for the liquid. We at first distribute gas and liquid separately into two symmetrical parallel microchannels, and then make them contact at this T-junction and this T-junction. So at the T-junction, the gas and the liquid contact with each other and to have different flow patterns. And usually we can have bubbles at the T-junction, and the bubbles can move along the microchannel to the outlet. So here we have two devices for the study here, M1 and M2. For M1, we have uniform cross-section for the microchannel. So for D0 should be D1, D2. And for M2, we follow the Morris law. So the D0, D1, and D2 follow this rule. And at first we use gas liquid, and for liquids we have low viscosity. Here we use gas and the liquid. For liquid we use glycerol water mixture, and we can find different flow patterns here. So here we have gas, and this way we have liquid. So gas and liquid contact at the T-junction. Here we have bubbles, and we have bubbles here. So for this kind of bubbles, the length of bubble are greater than the width of the microchannel. So here we have a long bubble. We usually name it as slug flow. And for this kind of bubble, we also call it as Taylor bubble. And we also have another form of bubbles here, very tiny bubbles. So the diameter of the bubble are smaller than the channel width. For this kind of, we have bubbly flow. So we can change the gas pressure, change the liquid flow rate, and the liquid viscosity to have the different flow patterns. So here we have the transition lines between bubbly flow and the slug flow. And the transition line depends on the liquid viscosity and depends on the gas pressure and the liquid flow rate. So here we would like to know if we can have uniform bubbles during the lumbering up. So even at this quite simple case, two parallel microchannel, and we symmetrical parallel microchannels here, we found that in some cases we can have uniform bubbles. Here we use CV to judge the uniform of bubbles. So here the definition for CV, coefficient of variation, listed here. So if CV is smaller than 5%, we can see that we have nearly uniform bubbles. And we can see that if we change the operating conditions, we can have uniform bubbles in some cases. So here we have dotted lines. So if the data below the dotted line, we have CV smaller than 5%, we have uniform bubbles. But in some cases, we can see that in some cases, for example, here with high gas pressure, with low liquid viscosity, we don't have uniform bubbles. So that you say that distribution of gas and the liquid in these two simple parallel microchannels are not uniform. So we would like to know the reason. So here, if we think about the prediction for the bubble size here, if we use the mechanism for bubble formation at T-junctions, we have squeezing mechanism and the shearing mechanism. In this way, we can correlate the bubble size with the operating conditions as stated previously. For example, here, the flow rate ratio between gas and the liquid, so Qg over Ql. And the capillary number. Capillary number is the ratio of the viscous force over surface tension force. So here we can correlate the bubble size with Qg over Ql and the Ca. And here for the gas phase, we use constant pressure control method. So we would like to correlate Qg with the pressure. So here we can use this equation, Hagen-Poiseuille equation, to correlate the pressure and the gas flow rate by using a hydrodynamic resistance R. And R related to the gas liquid two-phase flow status in microchannels. So as we can see from the previous slide, we have different gas and the liquid status in microchannels. For example, here we have different number of bubbles, the length of bubbles. So in this way, we can have the resistance, hydrodynamic resistance in microchannels. So if we have different size of bubbles in microchannels, we have different resistance. So in this way, we have, if we have different resistance in the two parallel microchannels, we have different operating conditions here. And then by using this equation, we have the different bubble lengths. So that you say the bubble formation at the T-junction is coupling with the hydrodynamic resistance in the downstream microchannels. And the hydrodynamic resistance depends on the gas liquid status in the microchannels. So in addition, we usually have collection chambers. For example, here we have a simple collection chamber like this triangle geometry here. And we can see that for different size of bubbles, we have different bubble behavior or bubble swarms behavior at the collection chamber. For example, here, if we have very tiny bubbles, the bubbles move towards the outlet in a certain route like this. So for this way, we can have uniform route for the bubbles, and we usually have uniform bubbles like this. And in some cases here, if we have large bubbles, the bubbles can collide with each other. And if they collide with each other, they can make difference of the resistance for different paths. For example, from this point to the outlet and this point to the outlet. If the bubble behavior is different in these two areas, they can result in the different resistance at these 2 points. So in this way, they can also change the resistance, the pressure value at these 2 points. So in this way, they can change the resistance, hydrodynamic resistance for these 2 parallel microchannels, and they can less results in the different size of the bubbles at the T-junctions. And in some cases, we can have more complicated behaviors. For example, here, the bubbles can break up. So they can also have, or they can also leads to complicated hydrodynamic resistance in the chambers. So next, we would like to study the bubble formation and the uniformity of bubbles in viscous fluids. So here we also use glycerol water solutions, but here we use higher concentration of glycerol, and the viscosity ranges between this value. So they are very high more than water. So we would like to know the gas liquid two-phase flow behavior and the behavior of bubbles in the same microchannels, symmetrical parallel microchannels. So here we have gas in this way and the liquid this way, and we trace the bubble formation process, and we can see that the bubble formation process have different stages. We can have retracting stage, squeezing stage, and a pinch-off stage. And for these two parallel microchannels, we also trace the bubble formation process, and we can see that the bubble formation process is different for these two parallel microchannels. So we would like to analyze the reason for the difference. So here, by using the similar model, we also have the hydrodynamic resistance in the downstream microchannel to have the R. So R depends on the number of bubbles, the length of bubbles, and the liquid viscosity, and the length of the microchannel, and the capillary number here, and the width of the channel. So by doing so, we can predict the resistance in each microchannel and the relative deviation of the bubble length in each microchannel. So here we can see that in some cases, we can also have uniform bubbles, but in some cases we cannot. So for these cases, if we have non-uniform bubbles, the resistance in the downstream microchannels are different from each other in the two parallel microchannels. And for the collection chamber here, we also have bubble swarms, and for tiny bubbles, for large bubbles, and we have two mechanisms. Here we have mechanism A. The liquid phase tends to compact the bubbles and unify the moving parts like this figure, to minimize the potential energy in the chamber. And the mechanism B, the bubbles tends to disperse to minimize the average resistance in the cavity. So these two mechanisms compromise in competition to determine the route of the bubbles. And they also change the resistance for these two parallel microchannels. And then we can also use this model to predict the bubble length in the two parallel microchannels. So here we use similar strategy to predict the bubble length L. So the bubble length also depends on the gas pressure, liquid flow rate, resistance in the parallel microchannels, and the capillary number. And we can feed in the data to have the prediction for bubble length in each microchannel and for and for each device M1 and M2. And usually we have more uniform bubbles in M2. So the next one, we would like to study the effect of viscoelasticity. So for this case, we change the property of the liquid phase by using PO here, polyethylene oxidized glycerol solutions here. We change the molecular weight for PO and change the concentration of PO. By doing so, we change the effective relaxation time for PO. So we can change the elasticity of the solution. We would like to know the effect of the elasticity on bubbles in the symmetrical parallel microchannels. And here we have bubble formation under different flow patterns, slug flow and the bubbly flow, and based on stream flow. And the flow patterns also depends on the gas flow rate, liquid flow rate, and the property of the liquid. So we can also have the transition lines for the flow patterns. And for bubble formation in slug flow and bubbly flow, we use high-speed camera to trace the bubble formation process and to study the bubble formation process. Here we can have different formation stage. For example, here expansion stage, collapsing stage, and the pinch-off stage by using characteristic length scale here. We use the width of the gaseous thread to have the different stages for bubble formation. And for bubbly flow here, we also have expansion stage, shearing stage, and the pinch-off stage. In addition, we have wetting stage for bubbly flow. So this wetting stage is resulted from the elasticity of the liquid phase. So here we analyze the force around the gaseous thread during bubble formation, and we found that during the last stage of bubble formation, so the pinch-off stage, due to the highly deformation of the gas-liquid interface, the elasticity take effect on the gas-liquid interface. So that is say, if the gas-liquid interface is highly deformed, we have the elastic effect on the gas-liquid interface. And then we also have the elastic effects on uniformity of bubbles between these two parallel microchannels. So by using CV, we can see that in some cases, we have quite uniform bubbles. So CV is less than 5%. But in some cases, we also have non-uniform bubbles. And at last, we also have a prediction for bubble size by taking into account the effect of the elasticity. So here we have Wiesenberg number, Wi. Wi is the ratio between elastic effect and the viscous effect. So here we have Wi. So in addition to QG over QL and the CA, we also have another dimensionless group Wi to predict the bubble length. So for different flow patterns, slug flow and the bubbly flow, we can have the prediction for bubble length in these two parallel microchannels. So the next case, we have the another kinds of complex fluids, shear-thinning fluids. So here we have CMC aqueous solutions. So this one is sodium carboxymethyl cellulose aqueous solutions. So for this case, the viscosity of the solution depends on the shear rate. So here we have the rheological property of the CMC solutions here. So we can use the parallel model to predict the relationship between viscosity and the shear rate. So here we have K and N. So K is the consistency. So for different solutions, we have K. And N, the flow index. This one is used to indicate the non-Newtonian property of the fluids. So if N equals to 1, we have Newtonian fluids. If N here, N is smaller than 1. So N, for this case, we have non-Newtonian fluids. So here, we also do similar experiment. But here, the interesting thing is that if we fixed the feeding pressure of the gas, and if we have constant liquid flow rate at given operating conditions, we have different flow patterns in these two parallel microchannels. So here, we have co-flow of the shear-thinning fluid and the gas in these two parallel microchannels, like this picture. And in this case, in channel 1, we have slug flow, we have long bubbles. But in channel 2, we have co-flow of gas and liquid. And here in this case, we have slug bubbles in channel 1 and channel 2, but with different bubble length. And here, for this case, we have slug flow in these two parallel microchannels. But here we have we can have nearly uniform bubbles for this case. And we can also have other situations. For example, here we can have short slug bubbles here, and we have long slug bubbles here in channel 2. So here, that you say in given operating conditions for gas pressure and the liquid flow rate, we have different flow patterns in the two parallel microchannels, and the flow patterns changed with time in given operating conditions. So here we can have, for example, we can have the bubble length for slug flow, and we can trace the bubble length with time. So here we can see that the bubble length changed with time in here channel 2 changed with time, and channel 1 here we usually have bubbles with certain length here. We have bubbles in channel 1. So for this case, we would like to know the reasons. So we have measured the gas pressure at the inlet of the gas phase. So we can see that the pressure changes with time. So here, we at first the the pressure increases with time and then to a maximum pressure, and then the pressure is relieved, so to decrease the pressure. So and then the pressure increases again with time. So here we have the phenomena of the shut-off pressure of gas on the gas-liquid two-phase flow in shear-thinning fluids in parallel microchannels. So that to say, the gas-liquid distribution changes with time, even in given gas and the liquid flow rates, or gas pressure and the liquid flow rates. And fortunately, we can have slug bubbles in both microchannels. So here we have pictures for bubbles in the two parallel microchannels on the slug flow. And we have different geometry of bubbles and the shape of bubbles. So here, for example, here for this case, at low concentration of CMC aqueous solution, the trailing edge curvature is similar to the leading edge curvature of the bubble here, like this case. And here for a higher CMC concentration, the trailing edge curvature tends to be 0. So for example here, we usually have a flat trailing edge here for a bubble. And for higher concentration, for example here for 1% CMC, the trailing edge curvature is unstable, and we usually have a very strange structure for the bubbles. So we can have different flow patterns in the two parallel microchannels to have flow patterns like this. So here we have different type. For example, here for these two parallel microchannels, we have AA here for these two shape of bubbles. And for this case, we have A and B. And for this case, we have B and B. And for this case, we have A, C, and B, C, and CC. So that to say, the bubble shape depends on the concentration of CMC aqueous solutions. So that to say, the bubble shape or the geometry of bubbles depends on the shear thinning property of fluids. And for the size of bubbles, here we also trace the size of bubbles with time. So we can see that even in a slug flow pattern, we have fluctuation of bubble length and the formation period. So with time here. So we can see that the bubble length changes with time. So for these kind of solutions. So we analyze the resources for the fluctuation of the bubble length. We can have external fluctuations. So for example, caused by flow sources such as pumps and the way for the feed of gas. And we also have internal pressure fluctuations, such as the bubble formation process, because in bubble formation process, we have the evolution of gas and the liquid interface. And another case is bubble swarms in the downstream collection chambers. And in some cases, we have stable stage. So here, in stable stage, we trace the bubble formation process in the two parallel microchannels. Here, we can see that by using the gas head as a characteristic length scale, we found that the growth rate of gas head between the two parallel microchannels is similar. And the bubbles in the cavity are combined in pairs, like this, in pairs, and flow out in groups to the outlet. And for unstable stages, for example, here we have an example to show the unstable stages. So here for these two bubble formation process, we can see that the growth rate of gas head in channel 2, the red dot here, channel 2, is faster. And there are 3 parallel moving rules for bubbles at the cavity. So the resistance on both sides of the cavity is unbalanced. So in this way, we have different resistance in the 2 rules. So we have different growth rate for bubble formation process. And last, we also would like to have prediction for bubble length. So here we use we also use flow rate ratio for gas and the liquid and the capillary number. But here, for shear-thinning fluids, the viscosity depends on shear rate. So here we use a characteristic shear rate for this system to predict the viscosity of the fluids. So eventually we have this kind of capillary number to predict the bubble length. So we can predict the bubble length in each microchannel. And the next case for complex fluids here, the yield stress fluids, we are working on this study. So for yield stress fluids, the interesting thing is that if the stress is lower than the critical yield stress, we have here, for example, here tau is smaller than tau 0. Tau 0 is the critical yield stress. The fluid should be in solid state. If the stress is greater than the critical yield stress here, tau is larger than tau 0, we have fluid-like status of the solution. And for this kind of fluids flowing in a microchannel, we have a plug flow pattern in the center of the microchannel. We have fluid-like moving status for the fluid in the other parts of the microchannel due to the distribution of the shear rate and the stress in the radius direction in microchannels. And here we use couple pore solutions for experiment with different concentrations. And we also measure the rheological property of the fluids. And even at fixed gas and the liquid flow rates, gas pressure and the liquid flow rates, we also have different flow patterns in the 2 parallel microchannels due to the complicated rheological property of fluids in the downstream microchannel and the complex gas-liquid status in the downstream microchannel. Here we have different flow patterns. And we can also have transition of the flow patterns. And we also trace a bubble length with time. We can also find that the length of bubbles changes with time. And we also have the period for bubble formation here. And the period decreasing this with time until we have a minimum value. And if we achieve the minimum value, the flow pattern changes from the slug flow into annular flow. So the flow pattern changes with time. So that to say, for the dispersion of gas in liquid in this kind of fluids, we have to do more than to make sure that the dispersion status is the desired one for us. So we are working on this project. And the next, I would like to introduce briefly other geometries. For example, here we have asymmetrical parallel microchannels. So here for this one, it's easy to increase the number of parallel microchannels. So that's why we designed the asymmetrical parallel microchannels. So we also use 2 parallel microchannels. So here for this one, we use gas for this one, and the liquid here we have this route. So we studied the flow patterns like this. We have unstable, stable, and filtration flow patterns. Here the flow patterns depends on liquid flow rate, liquid viscosity, and gas pressure. And we also studied the effects of cavity on stability. For example, here, the stability is the greatest for the devices without cavity. This one, the performance is better than the cavity at the rear, and is better than the cavity at the front. And the effects on bubble size, we study the operating conditions, the effects of the operating conditions on the bubble size. And we found that for high liquid flow rate and low gas flow rate, we can have more uniform bubbles. And for the devices, the uniform degree for bubbles follow this order. M4 with front and the rear cavity is greater than M3 with front cavity is greater than M2 with rear cavity is greater than M1 without cavity. But for this one, from previous slide, we can see that for this case, we have the most unstable flow patterns or gas liquid status. But for this one, we have the best uniformity of bubbles here for this one. So we have trade-off effects also for the distribution of gas and the liquid. So eventually we have the prediction for the bubble length in the 2 parallel microchannels by using the hydrodynamic resistant model like this. And another case about the branching parallel microchannels here. We use a T-junction to make contact of gas and a liquid, and we use additional channel to feed the continuous phase to change the distance between bubbles and to facilitate the distribution of bubbles in these parallel microchannels. So here we can see that we at first have a bubble, and we feed continuous phase, liquid phase, to increase the distance between bubbles and to facilitate the distribution of bubbles in these parallel microchannels. So here we have bubble behavior in these parallel microchannels, and we can have breakup and non-breakup of bubbles at the T-junctions. And in some cases, for example, here for this case, we have line uniform bubbles in the parallel branching microchannels. If we would like to increase the uniformity of bubbles, we have to do something. So here we use this microchannel to feed the liquid phase to increase the distance of bubbles to enhance the uniformity of bubbles. For example, here we have uniform bubbles in the parallel microchannels. The last case is the step emulsification microdevice. Here we use this geometry to produce bubbles. So here, this geometry, at first we have confinement effect, and if we use a step and you use a much larger space to release the confinement. In this case, we have 2.5 dimensional space for bubble formation. So for this case is used for droplet formation previously. And if we use this device to produce droplet, we can control the droplet size by controlling the depths of the steps. So here we would like to say if we can produce uniform bubbles by this geometry. So here we use a single microchannel with steps to produce bubbles, and we trace the bubble formation process and to connect the bubbles and to count the frequency for bubble formation and the bubble volume. Here we can see that the bubble volume depends on the operating conditions. So that's a difference between bubble formation and the droplet formation in this kind of device. So here, the droplet volume depends on the gas flow rate and the liquid flow rate and the liquid viscosity. So eventually we have the prediction for bubble volume by using a stages model here. And we would like to increase the number of channels to produce bubbles here. From 1 microchannel to 2 microchannels here, we have 2 microchannels. And we can see that we have different bubble size in the 2 parallel microchannels, because here we use liquid phase like this. Here we have liquid inlet and gas liquid outlet, and here we have gas inlet. So for gas, we have symmetrical distributor for gas, but for liquid phase, because liquid flow along this way, so we have different pressure at the outlet of these two microchannels. So that you say the resistance at these two outlet of the parallel microchannels is different. So we have different bubble size in the 2 parallel microchannels. And but the bubble formation process can work together. So here we have the compromise in competition mechanism. So we also call it mesoscale mechanism. So how about to increase the number of microchannels? So here we increase the number of microchannels from 1 to 10 parallel microchannels. And here we can have bubble formation in these parallel microchannels, but we cannot to ensure that we can have the same bubble formation process in each microchannel. For this case, for this device, we usually have 2 microchannels to produce bubbles at the same time. And for most time, we usually have a bubble formation in a single microchannel in turn. So here we have the bubble formation process in these 2 parallel microchannels, and we trace the bubble formation process, and the bubble size depends on the resistance at the outlet of the microchannel. And here, the resistance at the outlet of the microchannel depends on the bubble swarm status in the cavity. So we have different bubble swarm status here. So That to say, the resistance at the outlet of each parallel microchannel changes with the status of the bubble swarms at in the cavity, and the bubble formation in each microchannel work together to have compromise in competition status. So we also have mesoscale mechanism for the bubble formation in the parallel microchannels. So here we can see that we connect the bubble size in the 10 parallel microchannels. We can see that for these operating conditions, we have different bubble size in for different microchannel. So the bubble size depends on the status of the bubble swarms. Let's move to conclusion. So here in this study, we have the bubble dynamics in parallel microchannels involving complex fluids. So this study is helpful for the lumbering up of gas-liquid two-phase flow in the application of microchemical engineering and multi-phase microfluidics. And the interesting thing is the interfacial dynamics. So here we have the bubble formation process and the bubble swarms behaviors. And we also use mesoscale mechanism to explain the bubble formation in parallel microchannels. And I would like to thank the financial support from the National Natural Science Foundation of China and the teachers and the students in our group, Professor Yu Guangma and Dr. Chun Yinzhu, and these students, especially Zhang Chong and Qiu Yinshen, Shen Mi, Cong Duan, and Zhiwei Zhang, He Wang, and Xin Yu Ying. Okay, thanks for your attention. If any questions, I'm happy to discuss with you. Okay, thanks.
Thank you, Dr. Fu. So if our audience have any question, you can unmute yourself and ask your question directly to Dr. Fu.
Hi, Dr. Fu. This is Zhao Yan from University at Buffalo.
Okay. Hello.
Can you hear me okay?
Yeah, okay.
Yeah. Thank you very much for the very nice talk, and the bubble dynamics is very, very interesting topic. So in fact, I have two questions about your experimental setup or experimental observation. So from you show a lot of a bubble formation from your experimental observation. Yes, so anyone can work for my question. So in fact here, so you use the black color to highlight the interface between the bubble phase and the liquid phase, right?
Yes,
so
that's right.
I'm just curious, what is the technique that you use? So because if for my very intuitive feeling, so if we just use the density to distinguish the bubble phase and the liquid phase, then we cannot see that kind of very clear interface boundary. So here, I'm just wondering, what is the experimental technique that you have?
Here, we just use a high-speed camera to trace the bubble formation process. And we use light and cold fade light to provide the illumination for the capture of the process. So in this way, we can, such as something like we use camera to capture the gas-liquid interface. And then we use this picture to make analysis.
Okay, I see. So yeah, and my second question, in fact, is about the posterior stage after the bubble collapsed with. After the bubble go with each other. So here I can see that your bubble is very, very stable. So basically two bubbles won't collapse with each other, right? So how you make the control? Say, so here I notice you use the hydrogen gas and some other liquid. So say if we want to change to other like gas, will that work?
Yeah, very nice talk. Very nice question. Yeah, yeah. In fact, we cannot control the behavior of bubbles. Here, we just observe the behavior of bubbles by changing operating conditions.
Right.
But the bubble behaviors are very complicated. For example, here, in some cases, as you just said here, we can have very beautiful route for bubbles. But here, we cannot predict the route for bubbles. We just control the operating conditions to observe the phenomenon for this case. But in some cases, for example, here we have different bubble size and different collision status, and we even have some very nice self-organization status. For example, here in a much larger collection chamber, we can have different self-organization behavior of bubbles. So we can classify the self-organization behavior of bubbles in some cases, but in some cases we cannot. So the behavior of bubble swarms are very challenging here. But here we just use operating conditions to change the status and to observe the behaviors. And we would like to understand the underlying physics behind these beautiful behaviors. But we are trying to do that. Yeah. Thank you very much.
Yeah. So in fact, just to follow up here, I can see you have those some kind of organization of your bubbles. Then I'm wondering, this organization, this kind of pattern, is it just some kind of special like a phenomenon for the nitrogen and your liquid like system? Say if we use different like a gas system, can this kind of pattern organization still be generated?
Yeah, that's a good question. Yeah, we would like to learn from, for example, droplet behavior in for many droplets, and for learn from foams. For example, for foam, we also have very beautiful patterns. We would like to do that, but right now we just at the first stage to observe the behavior. We would like to learn some very for example, as you just suggested, some very classical mechanism for bubble swarms and for droplets collection or self-organization. If we have some classical mechanism, we can make more clear classification for the bubble swarms.
Yeah, thank you very much for the answers.
Yeah. Okay, thank you very much for your question.
Very nice talk.
So follow Jiayan's question on this slide. I'm just curious about how do you stabilize the interface? So the purpose is you generate uniform bubbles, right? So in simulation, we also can generate very uniform bubbles, but the interface between the bubbles is very, if you make the bubbles contact each other, the thin film between them is it's not stable. It's very easy to break up because the thickness is very small. So do you have any special method to stabilize this system?
Yeah, very good question. Yeah, that's right. Yeah. In fact, in our experiment, we add surfactant into the liquid solution. So surfactant. So for this case, if we add a surfactant into the solution, we can change the contact status between bubbles, because in between bubbles we have liquid film. If we have surfactant in the liquid phase, we can change the status of the gas-liquid interface. So in this way, we can have in some cases we can have like these uniform bubble patterns, and to prevent the chance for the coalescence of bubbles. But in some cases, especially with high liquid velocity, bubbles can break up, as you just said here. For some cases, we can have like this. If we have very high deformation for gas-liquid interface, the bubbles can break up in some cases. So the breakup and the coalescence are very complicated. Yeah. So we just can control in some cases, but in these complicated cases, we cannot control the process in for the operation. Yeah.
Okay. So any question from other audience? So
can I ask one more question if
Sure.
there is no more questions?
Sure.
from
Yeah,
others?
thank you.
So here, because this topic is very interesting to me. So here you do the gas and the liquid like two-phase flow. So I'm wondering if you have tried any kind of immiscible like a two fluids phase, like water and oil. So we can think like if we mix water and oil, we can also generate this kind of like a bubble type like organization.
Yeah, very good question. Yeah, in fact, we have worked on droplet also. So for example, for liquid and oil, for example, with some oils, we can have droplet. For example, here, if we have water in this way, we have oil in this way, we can have droplet. So for droplet, we also have similar phenomena, but for droplet, due to the difference in the surface tension between phases and the density between phases, we have different behaviors in some cases. For example, for droplet, especially in high viscosity fluids and complex fluids, we really have more complicated interfacial phenomena during the droplet formation process. We can have jetting flow pattern and the satellite droplets and more complicated phenomena, interfacial phenomena for droplet. We also have several publications for droplet.
Yeah, I will definitely read all those publications. Thank you very much.
Yeah, thank you very much. Yeah, thank you very much.
Yeah, so talking about the different fluids, and for example, I remember you plot a phase diagram when you started the shear-thinning behavior. Actually, you are using non-dimensional numbers, right?
Yeah, that's right.
So if you are using the Wittenberg number, the capillary number, this kind of thing,
yeah, that's right.
Does this results can apply to different fluids? For example, as you are changing fluid, but usually you can keep the dimensionless number the same, right?
Yeah, that's right. Yeah, that's a good question. Yeah, that's a very good question because we do experiment. So in fact, we can only see that if our results are used by others, if the operating condition for the range of the operating condition and the systems are similar to ours, you can safe to use our results. But if not, we cannot say certainly that the result are universal for others. Yeah, because we have this prediction from our data, but the form for the prediction, for example, here the size of the bubble with the dimensional groups, this form should be used by others, but with different parameters, fitting parameters, such as alpha, epsilon, beta, gamma, and so on. Yeah.
Okay. So my last question is about the when you're talking about the maybe you go to the slides 22.
22, here.
Maybe next one, 23.
Here.
Yeah. You trying to study the phase diagram about the different type of the bubbles. And I noticed that when you change the concentration of CMC, the pattern can be completely different. So I'm wondering if there's a smooth change of the phase diagram or is a sudden change.
Here, for example, here the shape, for example, the flow patterns should be similar. For example, for different CMC concentrations, we have slug bubbles, long bubbles, but in some places of the bubble, for example, at the rear of the bubbles, we have very different geometry. So for these cases, we also have similar phenomena for bubbles in conventional equipment. For example, in a large column, if we have bubbles in liquid, especially in shear-thinning fluids, we also have very beautiful or very different bubble shapes at the rear. For example, if we use very high concentration of CMC solution, we also have some very, very complicated structure at the rear of the bubbles. So this one should be resulted from the high viscosity and shear thinning property of fluids, maybe.
Yeah, so the channel material you're using is PDMS, right?
Here we use a PMMA.
Okay.
Another,
so I'm wondering if this kind of phase diagram or this results will be affected by the elasticity of your channel.
Yeah, that's a very good question. Yeah. If we use PDMS, the surface should be we should have swelling phenomenon, and we have the change of the wall during the experiment, especially in high pressure status. But in PMMA, because it's a quite have a quite property in solid status. So for this case, we maybe have very high Young modulus. So for this case, if we have a certain range for the pressure, the change of the wall should be not too obvious. Yeah.
Okay, makes sense.
Yeah, thank you.
Thank you, Dr. Fu. So
thank you, Dr. Lee. Okay.
If our audience have further questions, you can directly contact with Dr. Fu. Okay.
Yeah.
So then we will end here today. Thank you very much to give a very nice and interesting talk. So,
thank you, Dr. Lee. Thanks, Joanne. Okay. Thank you.
Thank you, Dr. Fu.
Thank you.